So some of you would recognize part of the content of this presentation. It's been in some of our research forums previously, but I'm trying to build on the discussions that we started with that, but also to provide an overview of the iron ore supply chain in general and where minerals processing fits into that. So to probably start off, it would be good to define what it is that we're talking about today. So when we refer to iron ore, we basically have these four types of materials or minerals: magnetite, hematite, goethite, and limonite. So they are all rich metallic iron ores or iron oxides, and vary in colour from dark grey, yellow, deep purple to a rusty red. The more rusty red it is, usually the higher the Fe grade, which is always great to know. So what's interesting about the iron ore market is that it's a commodity that's not really traded like other commodities, in the sense that it's very much still transactions between buyers and sellers in closed conference, closed meetings with lots of background negotiations, and the market itself is not very transparent. Challenge to the audience: go Google what the gold price is today, and it's easy to find. Go Google what the current iron ore price is, and it's going to be pretty convoluted to get to what the spot price is today. So the way the industry works is it uses benchmark indices that collect data every day from industry sources, and then that is used to calculate the spot price. So currently there are about 5 of these benchmark indices used in various circumstances. The most commonly used one in the iron ore industry is the Platts Iodex, or the Platts Index, and that refers to a 62% iron content fines product, cost and freight delivered to a China port, and updates at 5:30 p.m. in Singapore time. Another one that's frequently quoted in media is the Metal Bulletin, which is a similar 62% Fe fines product, but via the Tianjin port in China. And that updates at 6:30 p.m. Singapore time. So what's interesting about the Platts index is that the assessment is a standard that's based on iron ore fines at 62% Fe, but it is applied over a range of grades from about 60% Fe to 63.5% Fe. Please excuse the use of Fe, it's very common in the market instead of just repeatedly saying iron. It also, it was initially used for long-term pricing agreements, but it has more recently also been applied to floating price spot indexes. So the interesting thing about this is not origin specific, and it considers a number of very liquid, widely traded brands in the assessment of the spot market value of fines delivered to China. So brands are things like Yandy fines, and there's a whole competition in the market to actually develop your brand and gain market share for it. So the Platts Index was implemented in 2008 on a daily basis, and since 2010 it's been used for annual negotiations between iron ore producers and steel makers for contractual purposes. So to put this in perspective, historically iron ore pricing has been very flat, and it's only really from around the 2000s that there's been a sharp spike in iron ore pricing and then a subsequent slide again. The reason that this is also relevant is that iron ore is mainly used in the manufacture of steel, and the main driving factor for iron ore use and therefore is economic growth. It's used in infrastructure projects. So if economic growth is high, infrastructure projects tend to increase, and the use of iron ore required to produce steel as well. In recent years, the iron ore pricing has very much been driven by the economic growth in China. I've taken this as a bit of a background from the iron ore conference in 2015 to provide a view of the long-term outlook for iron ore. Over the last sort of century, steel production has increased from about 60 million tonnes per annum to about 1.6 billion tonnes in 2014. This increase is mainly during two periods, the 35 years after World War II, and then commencing in around 2000 to 2010, coupled with the China-driven boom, where their compound annual growth rate of steel output exceeded 17% per year. Globally, though, going forward, it's predicted that economic growth will average at around 3% per year, which is a lot slower than the 17% during that peak boom period. And it's also predicted that economic growth will be more centered in developing countries, specifically places like Brazil, India, Indonesia. And the steel industry is going to play an important role in this. If you just think about it, the construction and automotive sectors use 80% of the world's steel demand. And even though steel recycling is forecasted to increase to about 35% by 2025, it's not going to be enough to meet the demand. So if you look at the commodity cycle, it's a real interesting example of the sort of ups and downs and boom and bust, in the sense that for almost a century, the prices of mineral resources remained pretty low, and that really supported world economic growth. It was driven by the discovery of large, easily exploitable resources, and also mining technological improvements, bigger trucks, better processing technology, etc. In the early 21st century, 2000 to 2010, we saw a reversal of this trend, and both production and costs and prices increased significantly. The long-term trend as well, during the initial part of the century, the lower prices also meant that investment in capital expansion was largely flattened, and we were just unprepared for the Chinese boom that happened. Ever since then, though, it has encouraged new projects to be invested in, and the aim is to expand capacity, gain a market share, and also have a wider range of products to meet customer demand. In present years, though, especially since about 2014, the prices have declined and pretty much leveling out, and it's also predicted to remain like that going forward, if you refer to the previous slide again. It's also expected that Chinese growth will slow down, like I've already mentioned. All of this, though, while we're currently facing a decline in mining grades and ore quality, and pretty much the industry expectation at the moment is to produce whatever you're producing at a much lower operating cost. So in summary, this lowering of the overall cost curve was basically driven by decline in iron ore prices in recent years. It also will lead to lower sustaining capital being invested in the upcoming years. And there are growing environmental concerns around the entire supply chain regarding emissions, dust control, especially during the iron making process as well. There's been a huge focus on improving efficiency, and customers are willing to pay a premium for grade, although mining grades have actually declined. So the only way to bridge this gap is actually by focusing more on processing going forward to meet that market demand. Why is this important for us? Well, we're the largest exporter of iron ore in Australia. 25% of the world's reserves are situated in Australia, and we produce a quarter of the world's iron ore per year. Most of the mines are situated in Western Australia, but there are also some in South Australia and Tasmania. Before I go into the supply chain, I should probably also mention that iron ore is usually produced as a suite of products, and lump product being very sought after in the market, as that can be directly charged into a blast furnace. Lump products, all these products, the expectation is for it to be above 60% Fe, and it has a sizing requirement attached to it. So lump products usually around greater than 10 mil, less than 40 mils. Your fines product is less than 10 mils, and then you also have magnetite concentrate that gets sold on the market, and that's much finer. It requires finer grinding for processing, and the expectation there is that it's above 65% Fe with very low silica content. And then also pellets are widely sold in the market. It's either acid or basic pellet, and that requires a very tight sizing as well as a compressibility strength measurement for use in the blast furnace. So the key is that direct shipping ore, with the term direct shipping ore, is preferable. You want to process iron ore as little as possible and get it out of the door on grade. So there's a lot of focus around blending practices and how to blend different areas from your mine to achieve product grades consistently, because you've got one spec you've promised to the customer. Major diluents are silica, alumina, phosphorus, or silica oxide, alumina oxide, phosphorus, and sulfur. So if you look at the iron ore supply chain, a typical mine would have a variety of pits that are stockpiled, with blending being a key requirement of how it gets stockpiled, and crushed to meet a lump and fines product that's directly railed, stocked again and blended from the different mines, and shipped and exported to China mainly. So you've got one step to get it right, to get it on grade. Low grade iron ore, which is usually anything less than about 56% Fe, down to about 40 to 42%, gets stockpiled separately in the process. Again, in this beneficiation process, the aim is to produce your lump and fines products greater than 60% Fe, while maximizing your lump portion of it. Magnetite ore is processed separately, where it's then filtered either, well, usually pelletized for exporting, or if you export magnetite concentrate, it gets sintered and then fed to a blast furnace. So in the next couple of minutes, I'd like to spend some time on the beneficiation of low-grade iron ore. So low-grade iron ore is usually beneficiated using gravity separation. And that separation is achieved by the minerals that you're interested in, or the major components, having significant different specific gravities. The advantages of this technique is that it's economically, well, environmentally sustainable, economically pretty cheap to implement, and you can achieve really good separation. Some of the drawbacks of this process, though, is that it is a wet process. It uses quite a bit of water, and it is impacted by rheology effects, and it's very dependent on the separation efficiency is very dependent on your mineral texture, the liberation, and your sizing distribution that you're feeding to these units. So to illustrate, hematite would have a specific gravity in that range, where on the opposite end of the curve, your quartz, silica oxide bearing mineral, is about 2.5 to 2.6. That difference between that mineral specific gravity and the one you're interested in is what affects your separation. As your ore quality changes, though, the difference between these two ends shrink, and separation becomes more difficult. Other considerations that's really important is to understand that most iron ore deposits are what is called banded iron formations, which is basically sedimentary rocks composed of bedded iron oxide minerals with silicates and carbonates and carbonates as you gain. The degree of banding and the weathering really impacts your separation as well. And understanding this wall characteristic is key to understanding how your gravity separation plant is going to operate. And the aim, of course, again, is to crush this as little as possible and to maximize your lung production and meet that 60% airflow target. So equipment usually used includes spirals. Who's been panning for gold recently? Because that's basically the principle you're looking at. Just slightly less manual labor these days. But what it is you feed material down a trough, and it stratifies based on specific gravity. Now your lighter minerals in suspension move across the surface of the trough with higher tangential velocities to the outer rim, and your heavier non-suspended particles slide down the incline towards the center of the column. Now, this secondary flow has a certain capacity to lift and transport particles, and at a given size, the lower density particles have a higher probability of being lifted and transported away. Pretty simple. In practice, what you have is a spiral tower with a spiral start at the top, and basically these spirals going down until you extract the product at the bottom. At each one of these stages, you can off-take, concentrate. Okay. So your equipment variables include things like spiral pitch, the location and type of the splitters, the trough profile, the number of turns, and whether you're adding wash water and how much. It's very sensitive to changes in flow rate specifically, and usually these circuits are set up to have a constant flow rate to them. But it also is dependent on your feed size distribution and percent solids to achieve separation. Basically, your separation is mainly driven by density, but particle shape and size will also play a role. Your overall aim is to maintain adequate solids loading in your concentrate area in your middling section, but at a bulk density low enough that you still have mobility of your particles for separation. Feed distribution to your spirals again key, and usually these units run at about 6 to 8 tons per hour. And circuits are made up of banks of these ones, which usually use a very low footprint as well. And the ideal feed sizing is in the range of about less than 1.8 millimeters. But very importantly, the slimes fraction is removed from the feed using classification and not even processed. So there are a couple of ways that we can come up with efficiency curves to explain or try and predict plant performance given a specific ore characteristic or ore type. For spirals, we use a heavy liquid separation test as a proxy to determine a grade yield relationship. You can also use Wolfley table tests to try and predict or match plant performance. So for a heavy liquid separation test, you place your sample in a low SG liquid, and you split it into two fractions, either the floats and the sinks. The sinks is washed in solvent, dried, and then placed in a liquid with progressively higher specific gravity until you get a sink fraction that is small. All these fractions are dried, weighed and assayed, and then you can construct a grade yield relationship. What I wanted to highlight here, this is actually some data I had off to the side of an operation that the feed here is a similar head grade, but it was taken about 2 years apart. And you can definitely see that if you're aiming for a product of less than 5% silica, the amount of mass you can recover to concentrate is significantly less in the one example than the other. And that's really driven by the characteristics of the ore. And it's useful to have this information up front so that you know how to blend your material to maximize the visc curve, but also to understand how to set up your plant to achieve good performance. So for your coarse fractions though, we usually use jigs to separate them. So what this is just you fluidize your feed material by pulsating water, and then that results in the formation of layers in the jig. Now I've used one example here of what's previously called an all-mineral ore jig, and just because they've got the best marketing material available, it actually explains it pretty clearly. So what you have is a hutch with a screen deck and a feed bed being fed onto it. You have these three rotating valves, or rotary valves, that pulse air through the chambers into underneath this bed, and then basically lifts it. So you get hindered settling in both your up and down current, where on the up current your lighter particles move up faster, and on your down current your heavier particles settle out quicker. And by doing that, you can basically get separation. You can then use a float with fish weights on it. And this basically determines, it gives an apparent density, and it determines the cut between the top layer of the bed and the bottom layer. And then there's a gate that discharges your bottom layer, which contains your heavier minerals, and in this case hopefully our iron ore, into the hutch as product. So keys for operation for this unit is it needs to have a uniform feed to the unit, and you can set up your jigs dependent on the feed sizing you are providing it. So feed sizes ranges between 2 mils to 40 mils, but it's usually you're aiming for a tight size distribution to limit sizing effects on your separation. And your operating variables include things like bed level, your fish weight, your water flow rate and distribution between the different chambers, as well as whether you're using a ragging bed to capture or improve recovery of fines on your finer jig operations. Again, for jigs, we can perform a batch test using a lab scale cell, where you can add a sample and you can run it for 20 minutes when the material separates in layers. You can remove all the layers and then again dry away and assay them to construct a grade yield relationship, similar to the ones I've already shown. It again shows that same head grade, different timing, different areas in the pit. You get quite a different amount of mass recovered if you're aiming for 60% air feed product. Again, very important to understand this so that you can operate your plant efficiently. I'll just, for interest sake, put up a typical flow sheet of what a beneficiation plant would look like. You basically have the screening stage where you maximize the amount of lump into your lump circuit, into your lump jig. All other material goes to a fine screen, which splits it into a fines jig component. And then anything less than about 1 mil goes to a spiral plant. And spiral plants can have different configurations with roughing and scavenging stages as well as cleaning stages. And the key there is your middling stream on the spiral is the one where you haven't had clean separation, and you're trying to, on the rougher stage, try and actually process that through an additional scavenger, trying to improve your overall recovery without negatively impacting your grade too much. I'll move into just talking briefly about magnetite processing. In that space, we normally use magnetic separation. Now, separation here is achieved because a particle is either ferromagnetic or paramagnetic or non-magnetic. And again, these units require low capital cost, and they actually achieve excellent separation. If a particle is magnetic, and whether that's a composite particle or not, it will usually get recovered unless you're doing something terrible in terms of plant operation. Disadvantages though, very high water use. You've got limited operating variables that you can play with on site. And you have a very high recovery of middlings or locked particles if you're not careful. So just an example here, that is magnetite, that is chromite, hematite, and quartz again, with the different levels of field strength required to affect separation. So usually we would use drum separators, or wet magnetic drum separators, and you've got basic two tank styles, either counter-current flow or concurrent flow. With counter-current flow, the drum rotates in the opposite direction as feed. As your feed material is fed, your magnetics basically attach to the drum or connect on the drum, rotate out of the slurry field, but there's a magnetic scavenging zone at the bottom of the drum where you can get additional recovery. So these ones are usually used in a rougher type application. Your concurrent style, the drum rotates in the same direction as your feed flow, and your feed is channeled underneath the drum, and your magnetics connect on the drum and then is collected. This is usually for a cleaning stage. Your number of separation stages required to upgrade the material is really dependent on what the product grade is you're after. It's specifically driven by the silica oxide content in your final product. Your main operating variables on these ones, feed slurry density is the absolute key and has a big rheology impact. So the higher your rheology becomes, the more you will have entrained particles being rotated out of the stream with your magnetics particles as well. So lower feed density is really important for like cleaning stages to make sure you really don't have a lot of entrainment of non-magnetic particles. Feed flow rate or hydraulic capacity is another consideration, as well as your bath level, which basically determines how deeply the slurry is submerged in the rotating drum, and your squeeze gap, which is basically your off-take point of your magnetics from the drum. Again, we're always looking at finding ways of predicting what plant performance would do. Magnetics recovery is usually estimated using a magnetic susceptibility test, and StatMag is an instrument that's widely used. It measures total magnetic moment of a sample in a high magnetic field, and it determines magnetic mass content in the sample. And that's important because locked particles have an impact on the amount of mass you recover. It's very fast, it's reliable, repeatable, low cost, and it's used with relative good accuracy. You also have what we call a standard test, a Davis tube recovery test. And that's used to estimate magnetite recovery and product grade for a given particle size distribution. It consists of a 25mm tube, in-plane tube between the pole tips of the electromagnet. Material is sparsely tube while the tube oscillates, and magnetics are held by the magnetic field, and the non-magnetic or weakly magnetic material washes through. The two fractions are then dried by an assay as well. The key with this test though, the Davis tube recovery, is to understand that your sample preparation plays a key role in the result you're going to obtain at the end, where specifically your particle size reduction technique is of importance. It needs to simulate what your liberation is going to be like on the operation. Otherwise you will either overestimate or underestimate performance. This is probably a bit more of a modern flow sheet, where in recent years alternative comminution technology like high pressure grinding rolls are being used in iron as well. And the key to this flow sheet is, if you look at it, there's no recycling. It's like I've already said, if it's magnetic, the chance of it being recovered is extremely high. What you're really after here is rejecting the gangue mineral at the different stages. So you're trying to liberate your magnetic particles so you don't actually have a lot of composite particles being recovered to concentrate. So you'll have a number of grinding and wet magnetic separation stages with concentrates from those stages being subsequently ground down, recovered, ground down and recovered until you obtain your final product. So in summary, iron ore demand is mainly driven by world or global economic growth, and China will continue to play a dominant role in that space in the foreseeable future. Australia is the world's largest exporter of iron ore, hence it's important for us to really support that industry and understand what it is that drives their performance mechanisms. Iron ore deposits themselves are usually banded iron formations, and mainly economic deposits mainly consist of hematite and magnetite. Iron ore products are usually grouped into lump, fines, magnetite concentrate or pellets, all aiming for definitely above 60% Fe given current market conditions. And low-grade ore beneficiation is usually achieved using gravity separation, which is cheap, environmentally sustainable, but you have to really monitor separation efficiency by looking at your ore characteristics and your particle size that you're feeding into these units. Magnetite processing, on the other hand, is mainly done by wet magnetic separation at a much finer grind, and these units have very high efficiencies, and the magnetite processing or subsequent processing is then pelletized and sintered before being fed to the iron making process. Unfortunately, magnetic separation also comes at the cost of high water use. And the biggest challenge there is how do you manage middling particles or composite particles for liberation. I'd like to spend a little bit of time, this is probably the most interesting slide that everyone's been waiting for, and it's the so what. Going into understanding that the market has changed and that the aim now is for being a low-cost producer, but in an environment where we don't have the same resources available. A lot of the high-grade resources have been mined. Mined grades are deteriorating, and processing is going to become more and more important to achieve what the market demand is after, and that's a high-grade product. The customer is willing to pay a premium for it. So the only way to bridge that gap in my mind is to focus on how we process this material and making that more efficient. A couple of ideas there is definitely understand the mineralization of your ore so that you understand what's the right feed size distribution that you're aiming for to send to the different processing areas. As we go into lower grade ore bodies with more difficult mineralization, your gill-side and limonite content goes up, and you'd also see a lot more clay type minerals. The removal of slimes coatings on your valuable mineral particles, as well as breaking down of composite clay particles, is going to become really important going forward to maintain product grade. And classification improvements will always be key. The tighter your size distribution, you limit the amount sizing has an impact on your separation process, especially for gravity separation. Improved filtering and dewatering is going to always be key, something I didn't mention. Product moisture is a big challenge in certain ore deposits where we are bound to produce a fines product below a certain transportable moisture limit for it to be safe to be seaborne freight. And there's a lot of focus on trying to dewater some of these more difficult products. At the moment, the only way to solve it is to let it stand on a stockpile for a week, maybe two, before you rail and transport it for moisture to drain out. So there's definitely areas there that we can improve to have less inventory sitting on ground waiting for an acceptable moisture level before we can handle and export it. Historically, low-grade iron ore was mined coupled with high-grade ore, and as we all know, it goes to a low-grade dump, and no one really looks after it. So a lot of operations would have large low-grade dump deposits with very little geological or metallurgical data on what those dumps will perform like when you start processing them. There's a lot of scope to characterize that material and understand how we can process it. Also, efficient recovery of water for recycle. Both the, gravity separation and magnetic separation are water intensive, and the more of the water we can recover and recycle, especially considering that most of these operations are in water scarce areas, the better off we'd be. Recently, hematite tails dams reprocessing would also be the next logical step. The material is sitting there, it's been processed before, but using only gravity separation. So what other novel technologies can we apply? And things like high intensity magnetic separation could potentially recover hematite from those deposits. Also, as I've mentioned, the slimes fraction, or less than 45 micron, material is usually untouched and hasn't had a chance for separation. On top of that, in terms of magnetic separation, if we can develop a novel technology for low intensity dry magnetic separation that's similar in performance to the current wet process, we'd be well off in terms of improving overall productivity and cost. So I'll open the floor for questions, and I'd love to also hear your ideas about where to go to next. And this is just sort of my brain dump of things that definitely in my space I see benefit in.